Okay, so good morning, everyone, for this Crypto Cafe talk. So today we have an invited speaker from UCF, so Mireille Sassengelding. I met Mireille a few years ago when we were both working in Kazakhstan. So he has a variety of interest. So he's an applied mathematician, but he also has interests that go probably beyond the range of normal applied mathematics. So beside mathematical physics, he's also interested in quantum machine learning and bioneuroinformatics, mechatronics. He currently works as a research scholar and visiting professor at the University of Central Florida, the math department, and also he's a lead data scientist at Beldev Medical. Thank you very much for agreeing to give a talk, and we're looking forward to hearing you speak. So the floor is yours.
Give me a second. Am I audible? Can everyone hear me?
Yes, we can.
Yes.
Yeah.
Okay, perfect. Alrighty, let's get it started. My research is manifolded and it's entitled as variational quantum neural networks for modeling and solving heat and mass transfer problems. It's not directly related to cryptography, but the questions we're asking here are related to cryptography and cryptanalysis, and this is the reason why I decided to give a talk here. And I appreciate you guys hosting me here, and I thank everyone who made this possible, and Francesca. So yeah, these are the questions we're asking, particularly in this research, and we are particularly trying to solve and explore the ways how to address question number one. How can we easily solve heat and mass transfer problems with the help of quantum AI? When I say easily, it means that we would provide some methodology or a framework for engineers specifically, not to deal with mathematical formalism. And when I say solve, I mean finding a temperature function and or heat and flux function, heat flux function, and moving boundary. So we'll be dealing with the differential equation, partial differential equations, systems of partial differential equations. And where this research goes is to the second question and related questions to that. Can quantum AI actually build mathematical models? And can it actually create mathematical equations and solve them numerically and symbolically? And the way how I designed this presentation is I would like to let audience to ask questions during my presentation and to conduct it in a way in a form of discussion. Please feel free to stop me and ask your questions. So if we go back to the title, we're dealing with variational quantum neural networks, which which is some sort of a hybrid of classical and quantum computing. It's just a bunch of unitary operators we're dealing with, which are called gates. And the way how it works is it's not the way how it works, but probably where it goes is that it's industrially applicable. We can build artifacts, software for engineers based on this framework. So it's not a pure quantum computing, it's variational quantum computing, which I will elaborate on a little bit in a moment. So we're dealing with the heated mass transfer problems, and particularly with the Stefan problem. It's a partial differential equation with moving boundaries, but ultimately would like to go to the any kind of differential equation and actually to any kind of mathematical formalism through quantum AI. Okay. So this is the equation. This is an example. This is the so-called two-phase Stefan problem, a system of partial differential equations where temperature function has to be found, T1 and T2 temperature functions have to be found. And here, besides the temperature functions, we need to find either heat flux PT or alpha T, this boundary function, moving boundary function. It's not just the boundary. It's not. It's a moving boundary, and it's called free moving boundary. So these are initial conditions. These are boundary conditions. And this is the so-called Stefan condition. It's the energy balance. So this is the visualization of the physical phenomena. I gave as an example, it's an electrical contact. It's a low temperature plasma where I'll probably not go. So this is the mathematical formalism, and with which, oops, give me a second. Okay, so and here we are, the question we're asking is, how can we utilize AI and quantum computing to solve this kind of problems, not only numerically or approximately, and also symbolically, meaning that we would have a closed solution and give a solution in with the, I would say, analytically is the right word, I guess. So, like I said, the framework we utilize is AI and quantum computing. And particularly in AI, right now, one of the trends, well, it's been a while. In 2019, the paper was published by Raisia and Natal, Physics-Informed Neural Networks. And this is the framework we utilize here. And it's the kind of workhorse. And secondly, we use variational quantum circuits. It's the framework for hybrid quantum and classical computing. So why do we need quantum computing or quantum realm, I would say, in this and in general? We need it mostly for runtime complexity, for beating classical computers in terms of runtime and spatial complexity. Okay. And this is the paper, I'd probably call it seminal paper, Reis et al. And this is the architecture of the neural network, which solves differential equations, partial differential equations, and ordinary differential equations. So here we have multi-layer perceptron. It's a feed-forward neural network. And, oops, sorry. And here we have automatic differentiation. This is the probably something I would say new and a breakthrough in this study. I mean, in their study. And these are this box represents the residuals where this function, we know that neural networks are function approximators, and all this down here is a function approximator. U here is a function which we're looking for, or functions we're looking for. So if it's a heat equation or wave equation, or any other equation, Laplace equation, Navier-Stokes, whatever it could be, or actually any mathematical, I hate to say formalism, but any mathematical structure, would it be the right word to say functor? But it is approximated by this neural network, feed-forward neural network. And once we approximate, let's say in this particular study, it's a heat function, U, we do the differentiation here, and there's a specific way how to do that. And it's done through different kind of activation functions, like softmax function. And then that function, which is approximated here after differentiation, combination of differentiations, it is sent here. And here we calculate the loss function and take the total loss function. After doing that, we do the decision. Either it satisfies our epsilon, our accuracy. If it does, then we're done with our neural network. If not, then we continue this iterative process. So here's the optimization. This is the backpropagation procedure, and mostly done through the different optimization algorithms. And one of them is the gradient descent. Stochastic gradient, there are a lot of optimization methods. So, and yeah, what we're looking for in this neural network, what we're updating or what we're finding here are these weights, W's, and B's biases. So these weights and biases are updated through this entire procedure iteratively. Okay, so this is this was pins which we utilize for our framework, and this is the architecture of variational quantum circuit or ansatz. So here, let me go back. So this entire architecture is a representation of the feed-forward neural network. It's basically this DNN. It's basically this part. So we represent the feed-forward neural network through this quantum variational quantum ansatz. So it's just like these are the operators, and why it is variational. It's because we have variables, these theta 1s and theta 2s and so on. We have input value. It is encoded, quantum encoded, and there are different feature map procedures to do that. So we're bringing the data here, the classical data, we're encoding it quantumly here through different operators. Like R stands for rotation operator. Mostly it is done through the rotation operators. And here, this mapped here, and these are variational, oops, sorry, variational operators. So if here we were updating W and B, weights and biases, here we're updating these variational operators, these theta 1s, theta 2s, theta 3s. And here, these are in a lot of, this is just an example of variational quantum ansatz. It depends on the problem and it changes. Ansatz means some sort of auxiliary or helper circuit per se. And this one, in a lot of cases, represent C0 gate. And that gate is also a unitary operator, and it's just a bunch of matrices. And it is responsible for representing entanglement. So why do we need entanglement? Why do we need superposition? It's to, roughly saying, it's to optimize or speed up the process. So basically we're taking the complexity, we're hoping for the complexity of the computation grow exponentially. When I say grow exponentially, I mean speed up exponentially over classical one and beat the classical one. So we have several layers like that, and these represent layers. So once these all computations are done, they're fed to the measuring, and this entire computation collapses to the classical computation. That's pretty much it. So this is the variation quantum ansatz, and it is in our architecture. I'll show it in a moment. We are replacing this part with this part to speed up the process. And yeah, here, this is the architecture which we've built. And let me real quick go back to the problem statement and to the example, I would say, here. So here in the Stefan problem here, we have, again, functions we need to find T1, T2, flux function PT. Or if we're looking for function PT, this problem is called inverse Stefan problem, inverse two-phase Stefan problem. And if we are looking for this alpha T, not PT, PT is known, and we're looking for alpha T, T1, and T2. So we're looking for three functions. Then this problem is called direct Stefan problem. So when we're dealing with the direct and inverse Stefan problems, we're dealing with several functions we're looking for, like T1, T2, PT, or T1, T2, alpha T, in this particular example. And here, what we're doing is that this is the function approximator. This entire neural network and this entire architecture is dedicated to find this T1 function or heat function, just one heat function. So to find T1, T2, T3, T1, T2, and alpha T, or PT in the inverse case, we need to have 3 of these where this part is replaced with this part. And we end up with this architecture. So the blue box here is a quantum part, and the red boxes are classical parts. Since we're dealing with both quantum and classical, such kind of algorithms are sometimes called hybrid algorithms. Or here, if we even more specify it, it is a variational quantum algorithm or variational quantum neural network. So here, just this flow from here, this is a general framework. So from T1, from tau 1 to tau n, is the number of functions we need to find. Beta 1 all the way to beta m are the either boundary functions we're looking for, or boundary functions we're looking for, or flux functions we're looking for. And this one arrow here represents this entire problem. Sorry, not the entire problem. I want to say this architecture and this architecture. Here, this flow represents those two. And if we're looking for the T2, then we need to construct this and this together, blend them, and this would be this one, this flow. And for the alpha T function, it would be these, we call them forward pass. FP1 stands for forward pass. Once we do that, once all the functions represented by the feed-forward neural network here in quantum, we feed that they collapse through the measurements to the classical values, and then we take the derivatives, the combinations of derivatives, depending on the problem we're dealing with. So here, particularly, we're dealing with the heat equation. And then after taking the combinations of those derivatives, I stands for the identity function. We send it to the loss functions. We calculate them, then send to the loss function here, to the optimization, and send it back here. And this process iterates. If there are any questions, I can take questions. If not, then I'll just continue with these loss functions.
Okay, then I can add something. This auto differentiator that you have here, how is it implemented?
Yeah. So like I said previously, this, give me a sec, I keep losing my mouse, my pointer. So this is the neural network, and I mean, this feed-forward neural network, it represents a function, but that function here in between in these layers goes through the so-called activation function. Okay, so since it goes through the activation function, and the activation function, they use the trick there where when you take the derivative of that function, or you take double derivative of that function, as many derivatives you want, that function is represented as a combination of the original function. Is this part clear? This is very important. So again, here, this is the neuron, right? We have an activation function, which is, in a lot of cases, let's take softmax. It's the combination of exponential functions. So When you take its derivative, the output, the derivative of the exponential function is itself, you know. So it's not just the exponential function. It is e to the power of x divided by let's have a look at it. E to the power of x divided by 1 plus e to the power of x to my memory. So when you take derivative of that function, you'll get let me take a board and try to write it. Francesco,
So basically, in this automatic differentiation part, you basically encode your differential equation, right?
well, I wouldn't say it encodes, but it represents the differentiation. When they say automatic differentiation, they mean that it's not that computer is capable to take the limit of the function, you know, and apply all the mathematics. It doesn't work like that. They're just using it just happened that the activation function in the neural network, coincidentally, when you take the derivative of it, it's just the combination of itself. And I just want to real quick show you on the board if you want. I'm trying to find the board. Nope. Hmm.
I think it's fine. I get the general idea.
Okay, but yeah, it's this function e to the power of x. I'm writing in the chat 1 plus x. It's very simple. This is the activation function they use in the neuron. When you take the derivative of this function, it's going to be again a combination of these functions of e to the power of x, of this function itself. To my memory, it's going to be if it is, oops, oh, I guess I can, oops. I assume you can see my drawings.
Yeah.
Okay. So e to the power of x, 1 plus e to the power of x. This is the activation function there. In a lot of cases, they use it. No. Let's go with f x. I'm sorry, I'm using touchpad and so when you take derivative of fx, to my memory, I don't want to do the calculations, but to my memory, it's going to be fx 1 plus f or 1 minus f, something like that. But the point I'm trying to make, this is how the derivative is calculated. Did I answer your question, Francesca?
Yeah.
Okay. Okay, let's move forward, but I can't stop. Okay, there you go. Yeah, I will not go through this example. It's from low temperature plasma, physics related stuff, electrical engineering and physics related stuff. So this is just a couple of words. It's an example where we considered an equation, differential equation. Here it is it is new. It's not 2. This is the spherical problem, by the way. It's not, yeah, it's the spherical problem. And instead of 2, we have new because in the model, in the visualization I just showed you, it's a variable cross section. And here it is new. And it is a three-phase Stefan problem where you'll need to find T1, T2, T3. The third equation, there will be 2 moving boundaries, 2 free boundaries, which you need to find, meaning that in the architecture, we'll need to construct 3 neural networks, sorry, 5 neural networks. And here in the architecture, there needs to be 3 neural networks. When I say neural networks, I mean this 3 feed-forward neural networks. 3 for the heat function and 2 for the moving boundary. Yeah, this is an example, and this is the loss function. And these are the values of those loss functions. So here, let me go back. So this L, which is called total loss function, is here, this L. Okay. And these residuals, boundary condition loss, initial condition loss, and so on, those are these. So if you're familiar with physics-informed neural networks, then this should be clear. If not, please ask your questions. I'll try to clarify. That's pretty much it. And here we're looking for these questions. These are the open problems. It's the neurosymbolic variational quantum neural networks, meaning that we're looking for, in the context of this particular problem related to heat and mass transfer problems, we're looking for closed solution or analytical solution where we would have, well, when I say a solution, I mean temperature function and moving boundary function. Those to be represented not numerically, but analytically through formulas. Can we do that through quantum AI? And the second question is, can we actually generate a mathematical model of physical phenomena, here particularly heat and mass transfer problem? Can we actually generate Stefan type problems, like the equations? Could they be generated by generative pre-trained transformers? Those would be involved here. Neurosymbolically, not approximately, but through the actual mathematical equations. And can they be solved? So these are the questions. And one of the approaches is so-called Kolmogorov-Arnold representation theorem, which you all probably know from functional analysis, which states that any multivariable function can be represented with the single variable functions. And if we go back to the neural network here, this is if U is a multivariable function, and here, instead of these neurons, and the weights which are here and biases which are here on these arrows, if we replace them when I say them, I mean the activation functions. With the Kolmogorov-Arnold, what would I say? What would be the right word? Using the Kolmogorov-Arnold theorem and put here actually functions, and the approach there is at this stage of development of AI, neurosymbolic AI, is the splines to reconstruct the function itself. This is the idea at this point. And then this function U would be represented mathematically, not approximately or numerically. So having said that, we're dealing actually not only with the with heat problems or heat and transfer problems. This could be applied for any partial differential equations. And can we deal with the cryptographic and cryptanalysis related problems using this framework? This is the question I came with to this platform. And I again appreciate for hosting me. And this is how I would conclude my presentation. Thank you.
One question? Yeah, I have a quick one. I was just wondering, what, like computations or algorithms specifically give you the quantum speed up for the heat transfer problem?
I'm sorry, your voice is wobbling. I can't hear you clearly.
Can you speak up?
Yeah, I was wondering, where you get the quantum speed up? What computations or what algorithms for the heat transfer? Where you get the quantum speed up versus classical computers? Like what specific computations give you, why would you use a quantum computer? Like where did you get the speed up for this problem?
Right. I'm glad you asked this question. Yes, it's not proven. We did not analytically prove it that we didn't make any computations yet. We didn't make any that question related, research related on the runtime complexity or speed up. But normally the speed up happens here through the entanglement and through these C0 gates and superposition. But I can't tell you what kind of speed up is that? Is it a exponential or what kind of speed up? Like I said, we didn't do the research on that yet. It's not proven yet.
Maybe I have another question. So if you want to model it for in cryptography, probably you would replace the derivatives by things like difference equations or things like that. So have you thought of maybe discretizing, so having some kind of discrete version of your variational problems?
Mm-hmm. If I understood your question correctly, because the voice is wobbling, I still can't hear you clearly. So if you're asking about can we apply some different schemes for this particular problem or in general for variational problems? Is that correct?
Yeah, for cryptography especially.
Yeah, sure. It's even easier.
So for instance, I don't know, would you be able to replicate something like Shor's algorithm to compute discrete logs through a like group action for instance?
Shor's algorithm, to my memory, is based on the discrete Fourier transform and an inverse discrete Fourier transform. And you're asking about if we could apply this for discrete log problem?
Yeah, with some kind of
Through this
evolution equation, maybe discrete evolution equation.
Let me think.
So viewing this maybe as a kind of as a kind of group action.
Reduction, you said? Reduction, you said?
So group action.
Oh, okay. Okay. No, I don't. I'm not sure, to be honest. Let me think. It's a good question. But yeah, I'll put it that way. But the whole idea of this framework and this study is a neurosymbolic AI. This is where AI is moving right now. To get rid of that black box in neural networks in AI. And yeah, that's pretty much it. And I'm trying to connect your question. I'm trying to connect Shor's algorithm, trying to connect this framework which we developed and Shor's algorithm and discrete log algorithm, and kind of failing to do so. If you could elaborate a little bit more, maybe, but maybe we could discuss this later on.
And your question?
I have a simple question. Do you know if there is a simulation of this of such an algorithm on some I don't know, some quantum simulator or something like that?
Well,
Had people ever tried some of such? I know if it is in a circuit model, you can use probably one of the quantum thing like to simulate that, but for
right, variational quantum algorithms are already simulated. I mean, there are a bunch of them. Physics-informed neural networks are also done. You can find the codes on GitHub. But for the free moving boundaries, I didn't see any kind of simulations.
Okay.
Yeah, we're trying to do that on our GitHub account. If you're interested, we can talk about that, and we can provide you the access.
Okay, I see. So you're saying that for some variation of quantum algorithm, there are some already some simulation to do that, right? Probably on big computer or something. I didn't realize that.
Oh yeah, absolutely. Variational quantum algorithms is a whole direction and field, and it is adopted for industry. I mean, it's not something theoretical only, which is applicable on IBM or D-Wave computers, which are not applicable in anywhere because of the quantum devices, which we don't have. But it's the real stuff which you can apply in industrial in market actually.
Okay, thank you.
My pleasure.
Any other question? No? Okay, well, let's thank Mireille again. Thank you very much for your talk.
My pleasure. Thank you for having me and hosting me.
Yeah, let's hope to meet again at some point somewhere in Florida.
Yep. Absolutely.
Okay, so thank you, everybody, and so we'll see you next time.
Mhm. Bye.
Bye-bye.